All right, let me just write here. X, let's say, so this is another example. Rn minus origin, and y is Sn, the unit sphere, Sn minus 1, the unit sphere. So x1 up to xn in Rn, so that sum of xi squares is equal to 1. Okay. So claim is that x and y are homotopy equivalent. And we write it this way. So let I to be again the inclusion map. So this is the sphere into Rn minus the origin, which is just x, be the inclusion map. Sending any point to itself. Okay, inclusion map. And R to be the retraction from Rn minus the origin. So x to y. It is defined this way. Rx is just x divided by norm of x. So you send any point to the unit vector passing through that point. Since x is not 0, this map is well defined, and it maps the whole Rn minus 0 to the unit sphere. Pictorially, it is like this. So you choose any point here. You just map this point to the point joining the line segment, the line to the intersection point of the line segment joining x to identity. Okay, so Rx is this point, x divided by its norm. Okay, now these two maps gives a homotopy equivalence. Why is that? Well, you see, I composition R. So this is a map from the sphere to itself, and I composition identity at x is equal to what? This is just I of R of Ix. I is just identity function. I mean, it maps x to x. It is not the identity function, but it maps x to x. And Rx is just x divided by norm of x, but this is already in the sphere. So this is just 1. Therefore, x divided by 1 is just x. Therefore, our composition identity is the identity function of the sphere. What about the other one? I composition R. This is from Rn minus the origin into Rn minus the origin. And it is defined how? I composition Rx is just I of Rx. So this is just I of Rx is just x divided by norm of x. But now this is on the sphere, and identity I just maps any point on the sphere to itself. So it is this one. So it is basically the function R. This is not the identity function of the space X, right? So this composition is identity. This composition is not identity, but I composition R is homotopic to identity function of X via the homotopy. Just the line homotopy. Consider this one. So F from X cross I into X, F of XT is just 1 minus T X plus T times Rx. Okay, this is a well-defined map. One has to be careful, right? This is Rn minus 0. So you have to make sure that the image never takes the value 0, but that is clear. Why is that? Because you pick a point here, X, and then this is the sphere. Rx is this point, and this homotopy takes values on the line segment joining X to the point Rx, right? For any t between 0 and 1. Here t is between 0 and 1. Therefore, there is no danger that the value of f will be 0. Okay? And it is clear that when you plug 0 here, you just get x, which is just identity function of x at x. And when you plug 1, you just get Rx. Therefore, f is a homotopy from identity to R, which is I composition R of X. Therefore, both compositions are homotopic to the identity. The first composition is already the identity function. You don't need a homotopy, but for the second one, you need a homotopy. Peki. Şimdi bir tane proposition var. If F is a homotopiculus,
Hocam kamerayı değiştirebilir misiniz acaba?
pardon, değişmedi. Ben değiştirdim zannettim. If F is a homotopiculus, x0 is a point in X, and y0 is the image of x0, then F star, the induced homomorphism from the homotopy group of X at x0 to the homotopy group of Y at y0 is an isomorphism. Okay, is an isomorphism. Okay. Idea of the proof diyeyim. Idea of the proof. Tam proof'u vermeyeceğim. Şimdi diyelim ki F homotopik bulunuz. F is the homotopik bulunuz. Dolayısıyla there exists a G from Y to X so that F composition G is homotopic to identity of Y and G composition F is homotopic to the identity of X. Then this homotopy will induce, since these maps are homotopic, this will induce okay, so this will induce F composition G start on the fundamental group, right? This composition from Y to Y, and it is homotopic to the identity function. Therefore, this will be just the homomorphism induced by the identity function. That is just the identity homomorphism of pi1 of Y at Y0. And similarly, the homomorphism induced by this will be just the homomorphism induced by the identity function, which is just the identity homomorphism. But this is not a proof. Basically, this is the idea of the proof, but not a complete proof. The reason is that, you know, the homotopy here doesn't, you know, have to keep the base points fixed. So if the proof would be complete if the homotopies would fix the base points at all times. But still, you know, one can prove that. I mean, they are, however, one can modify I mean, the homotopy so that we obtain an isomorphism. Isomorphism değil de we obtain the identity map. Şöyle yapayım. Yani buradaki sorun şu, elimde bir tane, şimdi şöyle yapalım, rastgele bir uzay alayım, bir Z uzayı, bir tane de base point'im var, buradan buraya bir tane fonksiyonum var. F diyelim. F identity homotopik. Identity homotopik. Yani bizim durumumuz bu. Identity homotopik. This is the identity function. Ama bu identity ya homotopik olan, so take an arbitrary base space and a map from this space to itself, keeping this fixed point, I mean base point, and suppose that these are homotopic. But the homotopy F may not fix the endpoint. So suppose that this is not necessarily x0. So let's say this is beta t. Okay. Yani bu x0 noktası diyelim ki dolaşıyor. Sonunda tabii ki gene şeye gelecek. Çünkü bu ikisi de z0 z0'e götürecek. In this case, still, you know, we obtain an isomorphism.
Sir, t is in what interval over here? I cannot properly see it.
0, 1. So it is the, you know, homotopy. So I have f here. Here, let's say I have f, and here I have the identity function. But the base point, let's say the base point is over here, z0. This point, my homotopy is not constant at this point. So it just travels a path, beta. Okay. Therefore, you know, although F induces a map from this fundamental group to this fundamental group, at intermediate times, I don't get a homomorphism from the fundamental group based at Z0 to the fundamental group at Z0, because the point Z0 is not kept fixed. It is just moving, okay? Therefore, one has to be careful, but still the conclusion of the proposition is true. But I will not, you know, talk about it more. I'll just leave it like this, okay? But just keep this in mind, okay? You can just look up any algebraic topology book and see, you know, details there. I will not spend time on that. Okay, another basic fact about fundamental groups is this one, product spaces. Let x0 and y0 be path connected based spaces. Then x times y with base point x0 comma y0 is a path connected based map based space, and pi1 x times y based at x0 y0 is isomorphic to the product of these groups, okay? Here I have the product of topological spaces, base topological spaces. Here I have the product of groups, okay? And we have isomorphism, okay? The proof of this is not
Sir, over here, do we have the free product of groups or
no,
some
no, no.
other kind of
Cartesian
product?
Cartesian products, not free products. Cartesian product of two groups. So, I mean, the distinction is this. Here, so for example, okay, so let me do one example here. Consider two torus. This is just circle times circle, right? I can just consider torus as just one circle multiplied with another circle. You just take a circle in the space and then just carry this circle over another circle, form a complete revolution, you will obtain the torus. Therefore, torus is just circle times circle, okay? And the fundamental group of the torus is just isomorphic, the fundamental group of circle times fundamental group of the circle. Therefore, it is just Z cross Z. The direct product, okay, direct product. I can also regard this, since it's an abelian group, just the direct sum of these two groups. But it is not the free product, okay? Free product is something completely different. Here we have Cartesian product. And let me talk about the proof a little bit. So proof, okay, now consider the map. I mean, homomorphism actually. I just call everything map, but sometimes they're homeomorphism, sometimes they're continuous maps, sometimes they're homomorphisms. You just, you know, understand what's going on from the context given by. So this is a map. It will be a homomorphism from this product of groups to this group defined by the following formula. So if I have two homotopic classes, then I just consider the homotopic class of the product map, okay? Where gamma 1 and gamma 2 are just maps, are loops at x0 and y0 respectively. And what is this path? Of course, this path is just gamma 1, gamma 2 at t, not t, s. This is just gamma 1 of s and gamma 2 of s. Okay. First, one has to prove that this is a group homomorphism. I will leave this as an exercise. Proof is exercise. But let me give you a hint. Think of the projection maps. Maps P sub x from x cross y into x, projecting onto the factor x and projection onto the factor y. Okay. So using this maps, you can show that it's really a group homomorphism. Bu size bıraktığım şeyleri hani sınavda falan sormam. Bunları hani bir algebreik topoloji kitabından şöyle bir bakıp kabaca anlasanız yeterli. Şuna aslında isomorfizm diyeyim. Grup isomorfizm diyeyim şuna. Yani ispatı size bırakmış oldum ama bir tane örnek orada yaptım gerçi torus örneğini. Bu torus örneği gerçekten güzel bir örnek. Hani pi1 bu z times z. Mesela şunu nasıl görürsünüz? Atıyorum. Bir üç loop'unu. Bu ne demek? Yani circle'ın biri, so this loop corresponding to 1, 3 means what? It's a loop that goes once around this circle and 3 times around that circle. So it's something like this. It just goes like this, and then okay. So it goes once in this direction, but 3 times in the other direction. On the rectangle description of the torus, remember I can obtain the torus by just gluing the ends of this rectangle, right, like this, and this path corresponds to the following. So just start from this point and divide this into 3 pieces, 1/3, 2/3, 1/3, 2/3. So this is 1/3, sorry, 1/3. This is 2/3. And then just consider the following path. You go like this, and then this point is glued to this point, of course. So you are at this point, and then you just follow this line, and then this point is just glued to this point, so you are at this point, and then you just take this line segment, and this point is of course glued to this point, but this point is glued to this point, so you completed one circle. Okay, this is just one circle, and it is this one, which goes 3 times along the direction A and just once along the direction B. Okay. And what is nice about this curve doesn't intersect itself. It's a embedded circle on the torus. And actually, let me give you as an exercise. Okay. The homotopy class of m comma n in the fundamental group, okay? In the fundamental group. So a pair of integers is represented by an embedded circle if and only if these two integers are relatively prime, okay? Otherwise, if you draw these lines, they will intersect each other, okay? So there is some arithmetic here. Efendim? Evet, evet. Bu aslında şeye kadar gidiyor bir yerde. Torus'un bütün homeomorfizmleri bu grubun Z çarpı Z'nin bütün izomorfizmalarıyla birebir eşlemeye kadar gidiyor. Yani bir yerde torus'un homeomorfizmleri SL2Z homeomorfizmleri ama up to homotopi gibi görmek lazım. Aslında homotopi de değil, tam o izotopi diyoruz. Ama torus'un bütün mapleri sonuçta işte Z çarpı Z'nin otomorfizmleriyle classify ediliyor. Öyle diyebiliriz. Onlar da işte 2 by 2 invertible matrisler over integers. Yani SL2Z. O da matematikte yani topolojinin bir dalı, o çalışma konusu mapping class group diye geçiyor. Bizim burada o işlerin piri olan adam da Mustafa Korkmaz. Hani onları çok iyi bilir. Tabii sadece torus yok. Bütün surface'lar var. Pi1 of Sn at any point is just trivial if n is greater than 2 or equal to 2. Bunu yapalım. Let x0 x be any point in x different than this base point. Base point. Choose a small ball. Small ball. Be in Sn around x so that x0 is not in that ball. So here is the picture. This is the sphere, let's say, and my x0 is somewhere here, and my x here, and I pick a ball around this point x. Okay. Let gamma be a loop at x0. So it's a typical element of the fundamental group. Tabii bu biraz garip oldu. Böyle bir pet olmaz, değil mi? At x0. Okay. Şöyle yapalım. Then, okay, now since gamma is continuous, the inverse image of this ball is an open subset of the domain of gamma, which is just 0, 1, interval 0, 1. Okay. Note that 0 and 1 are not in this pre-image, since gamma 0 and gamma 1 are both equal to x0, and x0 is not in B. Okay. Well, this is an open set in the interval 0, 1. Open sets are just open intervals, right? Disjoint union of open intervals intersected with 0, 1. Therefore, hence, this thing is a disjoint union of open intervals in the closed interval 0, 1, but I know that the endpoints are not in B. Therefore, those intervals should lie inside the open interval. Okay. So they are really open intervals in the open interval 0, 1. How many of them? Well, we don't know. There might be infinitely many intervals. Of course, countably many, because you cannot just put in R uncountably many intervals, disjoint intervals. Okay. Yeah, of course. Well, each open interval contains a rational number, and then yeah, if you index those intervals by rational numbers, then they have to be countable. Efendim? Yeah. we use results from advanced calculus and real analysis, right? 349. Okay, now on the other hand, this set, inverse image of the point X, is closed in the interval 0, 1, which is a compact set. Therefore, this is also compact. And hence, efendim? Yeah. Closed interval 0, 1. And hence is compact. Well, since it is compact and it is clearly contained in, since of course this is contained in this set because X is contained in B, and this gadget is a disjoint union of open intervals containing this compact set. It is not an element, it is subset. We see that this gadget is contained in the union of finitely many disjoint open intervals contained in this set. So there are finitely many open intervals. This thing is a countable union, possibly countable union of intervals like this. This is a countable set, and finitely many of them, which finitely many, I don't know, but I can just relabel them and say A1, B1 up to AK, BK. This intervals covers this set. Okay. And I know that these are away from the endpoints of the interval. So we have something like this. Here is my interval 0, 1, and my intervals A1, B1 is something like this. A2, B2 is something like this. And I have AK, let's say BK. Open intervals, okay? Now, each of these open intervals are mapped into the set B, of course, right? Each of these intervals are mapped to the set B. And what is B? B is a ball. B is a ball. Okay, let me just draw the B. This is the ball in the sphere. And the center is X. And this all these paths contained here, so they are, things like this. So the image of A1, B1 is something like this. Maybe A2, B2 is something like this. A3, B3 is something like this. There are some paths passing through X, the point X. what can I do? I can do the following. Since there are only finitely many of them, I can just push all these paths. Let me just draw, for example, one of them. Suppose I have a path like this. I can just push this path via a homotopy of this point, and then just, push it for more and more. There more and more to the boundary, keeping the endpoint fixed. So I keep the endpoint fixed, but just push this path of this point, and at the end of the homotopy, this path lies on this boundary of this ball. Okay, so I can just push all of them to the boundary of the ball. So via a homotopy, via homotopies, we may push the paths gamma restricted to AI, BI to the boundary of the ball. Okay, to the boundary of this ball. Yani diskin içinde homotopi yazmak tabii çok trivial bir iş değil. Biraz uğraşmak lazım ama hani yani şey görebiliyorsunuz. Şuradan geçen bir tane pet varsa bunu hafiften ittirerek böyle şey yapabilirim. X noktasından sıyırıp ondan sonra da diskin sınırına ittirebilirim. Yani aslında şöyle bir şey bile yazabilirsiniz. Şu iki noktayı sabit bırakacak şekilde şöyle şey yapın. Her bir buradaki sınırdaki noktayı işte şuradaki bir şeye point'e lineer olarak böyle zaman içinde gönderin. Yani bu diskin tamamını ittirerek şu yaya map edebilirim. Tamam mı? Tabii n'in 1 olmaması burada şu nesnenin 2 boyutlu olduğunu gösteriyor. O yüzden böyle bir resim çizebiliyorum. Öbür türlü böyle bir resim olmayacak. Zamanı bitirmişim tabii ki. Bir tek şey söyleyeyim, yani bundan sonra ispat bitiyor. Hızlıca söyleyeyim, onu bitsin. Bunun başka ispatları da var ama hani bu en şık ispatlardan birisi bence. Yani this way we obtain a loop gamma prime so that yani gamma prime'la gamma'nın homotopi klasları aynı in pi1 Sn x0, değil mi? Homotopi ile çünkü değiştirdim. And gamma prime is contained in Sn minus b. Yani bu diskin, değil mi, dışında kaldı. Open diskin dışında kaldı. Ama bu diskten, so when you subtract, if you delete a ball from the sphere, so you puncture the sphere, then this thing is contractible. So Sn minus B is contractible, and thus pi 1 Sn minus B is just the trivial group. So we have something like this. This homotopy class. So I have this inclusion map, and this gives a homomorphism, and my homotopy class of gamma, so gamma prime lives here because it's inside in the set, and it is mapped to, of course, just itself, which is the homotopy class of gamma. But I know that since this space is contractible, this is just a trivial group. Therefore, this element here is the trivial element. Therefore, via a homomorphism, this is a group homomorphism. So if this is I, this is just I star. It's mapped to E, of course. Therefore, this homotopy class is just the identity element in this group. Therefore, this element is identity. But this was an arbitrary element in this group. Therefore, this whole group is just the identity group. Okay? It has only the identity element. So that's the proof. Okay. Well, let me stop.